So far, we've had a conversation about how you can fit two right angle triangles on top of each other. That when you do that, you can consider the double angle that is made as a result. For example, the double angle, I believe it's here, right here at the top, alpha plus beta, which produces this large right angle triangle in here. Large as a result of it being in this picture, of course, and not in real life. It is purely dependent on which problem you're trying to solve. And that this right angle triangle that's made has an angle, alpha plus beta or beta plus alpha. And if you want to consider it in terms of sine, this BC is its opposite, its hypotenuse is AB. If you wanted to consider in terms of cos, then its adjacent will be AC, whilst its hypotenuse would still be AB. And then what we did is we took some rules. So we said, of course, let's say that the hypotenuse of this is of a length 1. We said that to aid in scaling later. We said that the adjacent of the top is equal to the hypotenuse of the bottom. We also found a secretive little triangle, right angle triangle in here, which we can utilize later. And then we get this diagram. And then from there, from this diagram, we've been able to pick things apart. The first thing we realize is that cos beta is equal to that adjacent side. So this black line here is just cos beta. We made a note of that. We said this can need forevermore be called cos beta. And we also were able to find out e to the f, for which we did. We found out that e to the f, utilizing some basic trigonometry, if sine alpha is opposite divided by hypotenuse, substituting what we know, particularly this rule about a being cos beta. A little bit, this should say cos beta. My apologies about that mistake there. A little bit of manipulation allowed us for this to be sine A cos B for this length here. Now let's go further. Let's consider sine beta this time. So I'm looking at the top triangle this time. The top triangle I'm going to make a little bit more clearer with some what perhaps looks like gold. Sine theta is now going to be sine beta, because I've picked this angle. I've been much more specific. I've picked this angle, and that angle beta, if I'm going to look at the opposite and hypotenuse of that top triangle, first of all, we have mentioned hopefully multiple times now, so you're starting to feel comfortable with this idea that the length AB is 1. The adjacent we care not about for now, we'll care for it later. This side is the opposite side. So sine beta is opposite divided by hypotenuse, but hypotenuse is 1, leaving opposite divided by 1, which is just opposite. So sine beta is just opposite. And of course, then I can, instead of leaving this labeled as O or even BE, I can say, well, it's now sine beta, B being a representation of beta. And to be more specific, instead of O, of course, it is the length BE. So sine beta is equal to BE. And therefore, any time you see BE going forward, we can substitute it for sine beta if we wish to. Okay, so I've made a couple of statements here. The first statement I've made is be aware that DE is parallel to CF. So D, hopefully, if let's double down on this concept by making it clear. There is a DE in there. If I go back, we've lost some colorage. So there is DE in there. And I'm suggesting to you that it is parallel to CF. And as it is parallel to CF, therefore, it must be parallel to AF as well. If they are parallel, hopefully this might aid in this conversation. That's probably not the straightest of lines, but it will do for now. If they are parallel, then I can make this diagram. And we've hopefully seen this diagram manifest itself in some angle problems. This angle, therefore, must be the same as this angle, therefore, right? And so, therefore, I said, therefore, the angle alpha appears in two other fundamental positions. Fundamental position 1, if I zoom in, is this angle, there, that angle, AED, that angle in here. This is the same as the angle alpha. That's the first place. The second place, I've made this obvious, but this is obvious mainly just because of the labeling of it. But the second place is that this is also alpha. This up there is also alpha. And why might that be? Well, the answer to that is to consider the following concept. This angle is 90 degrees. We are aware of that. I'm just going to take this triangle out. Imagine, if you will, that this BD, let's try and make this slightly smaller so that it is a little bit more graceful. There we go. This angle, this length BD, just reverted back to its old. It protested. I had a protest there. BD, and imagine I'm going to say that this is the equivalent of BD. There's BD. And DE, I'm going to say this is the equivalent of DE there, and therefore BE is going to be this, to aid in perhaps making sure that that is easier to understand going forward as I add a little bit more complexity. Let's throw in these letters like so. Okay, so first of all, we know that this in here is 90 degrees. So I'm just going to make this perfectly clear. Let's get the base black and say that in there is 90 degrees. That again is extraordinarily large, but I'm zoomed in quite a bit, so I'm not going to complain too much. Let's just leave that as 90 degrees in there. This angle, I do it quite large, from here around to here, that is 90 degrees, because it's a right angle triangle. So if I want instead from here around to here, then what I need to describe is this as, it will be the 90 degrees, the whole thing, it'll be the 90 degrees, take away this in here, right? No, sorry, I made that was incorrect a little bit to the degree. It will be the 90 degrees, the whole thing, take away this angle in here. And so what is that angle in here? We just had that discussion that if that is alpha, then this is alpha. So we can conclude for now that this must be the 90 degrees, take away, again I'm using A instead of alpha, the alpha. That's what that is in there. And finally, therefore, this up here, which is the one I'm trying to prove, I'm going to say is x. Let's say we don't really know what it is, it's x. To conclude with this part of our video, let's do a little bit of algebra. We know that the angles in a triangle are up to 180 degrees. That 180 degrees now must be x plus 90. So I'm going to plus that 90 degrees, that's the 90 degrees that's manifesting itself here, plus this angle in here, which is the full 90 degrees, take away this bit. So let's make this a color there. I'm going to take away this. And what is that? That is this. They are equal. They are the same. So it is that 90 degrees, the full 90, take away that alpha. And so let's finish that part off by saying, okay, plus, and then we're going to do 90 minus that alpha there. And then just recognize it's come slightly off screen. 90 plus 90 is 180. So we can say that 180 is equal to x plus 180 minus a. With a little bit of algebra, you can say you've got 180, these can cancel, that's one way you can look at it, or you can minus 180 from the right hand side, meaning that there will be 0 on the left. It's up to you how you wish to analyze that as a problem, but then we'd be left with 0 is equal to x minus a. Another way of writing that is to say that I can plus a on both sides. 0 plus a is a, so I'd have a equals x. And what was a all along? A was this angle, which was meant to be a representation of alpha again. So there is alpha, and now to conclude for this part of this video, I have shown you that this here is also alpha. And that is what I mean when I utilize the phrase I said here, therefore the angle alpha appears in two other fundamental positions. And what did I mean by that? I meant that the first fundamental position it appears is in here, AED, given that it was here as well, it must be AED. And the second fundamental position it appears is up here. That is also alpha. Right, that is also alpha. Thank you very much for bearing with me on that one. Now we can move on to trying to get to the final part of our sine double angle formula conversation, and then have a go at tackling and applying it to this problem.